is because they already believe it to be true. For example,
Good morning. Uh, there we go. So, due to a couple extensions and me being also incredibly busy, the tests have not yet been completely marked, but I will have the grades out by at least Friday by the latest, probably within the next couple days. Half of them are marked, and so far they do look really good. So it's great to see. Um, so we're just gonna keep going on with the material. Assignment 5 is released. I will get some additional practice exercises for predicate logic translation by Friday as well. Um, if you have any questions about assignment 5, we can cover them at the end of class, or we can do them on Friday. It's not due until next Friday, so you still have a week and a half. Um, and yeah, that'll be assignment 5. Assignment 6 will be the last one. There will be a test following that, and then it's the end of the course where we're pretty much getting to the end of it with these last few lectures. And scope ambiguity here is where we start to come full circle and tie everything together. So, although we've seen scope ambiguity quite a few times already, we're finally going to take a look at how we can do this syntactically. And not today, but on Friday, we're going to actually see how we can use compositional semantics rule by rule in our big trees like we did in lecture 6 to how we can compute the meanings of scope ambiguous sentence. So a scope ambiguous sentence is true if and only if, so and so is in the set of blah, blah, blah. Okay. So just to review some things, I didn't want to just do a total review of scope ambiguity because we've seen the same stuff so many times with the drawings of the two lines and the dots and circles. So I've added a couple new bits of information here as we go along and repeat the things just so we're definitely on the same page. The sentence "everyone loves someone," of course, is scope ambiguous. So we have the two different readings. We have the readings where of course, all I wrote it with the universal quantifier. uh, all scopes over um, some and some scopes over all. So a new term, maybe I have used this term before, but there's called wide scope and narrow scope. So these are usually the terms that we use. We pick a particular quantifier and we say that that quantifier has either wide scope or narrow scope. So in this example, we could say that the universal quantifier has wide scope. And this just means that it has the biggest scope of them all. Or we could pick the existential quantifier here, existential, and say that this has narrow scope. And this just means that it is scoping over the smallest amount of things in that sentence. And we can distinguish between the two interpretations by saying, which one has wide scope and which one has narrow scope. So, for example, in the second interpretation, this is the interpretation where the universal has narrow scope. So there's one interpretation where the universal has wide scope and one interpretation where the universal has narrow scope. Or you could say there is one interpretation where the universal has wide scope and there's one interpretation where the existential has wide scope. So we can use wide and narrow with each of the quantifiers, and this will give us specific information about uh, which interpretation we're looking at. Of course, we can just use the term that all scopes over some or some scopes over all, but this is more syntaxy. in terms of how we speak about these sentences. So regarding entailment as well, there's also an entailment relation between these two different interpretations. And I will actually draw this out yet again. Um, so the specific situation, the most narrow reading of the universal, is going to entail the general reading of the universal, but not vice versa. So I will illustrate this. Imagine we have a situation where there is a particular thing or a particular person that every single other person loves. So this is the there exists a y for all x reading. There's some particular person that everyone loves. Okay, so if we start with this interpretation and we add more possibilities for these people to love, this still satisfies the condition of the for all x and exists a y interpretation, the universal wide scope interpretation. So it still satisfies the fact that every person loves some person or other. It just happens to be the case that every person in the universe happens to love one particular person. But it still satisfies the condition that each person in our world loves some person or other. So um, if we were to like draw our little set diagram of here's all the different situations that satisfy. I guess there's really only one situation where this works. And here's like all the different possible ways that we could make for all x exists a y work. Then there's like this entailment relationship because that specific situation is within the general situation. But the entailment is not in the reverse direction. So this is more like a one. It's a theoretical fact of language and mathematics. That one entails the other. But also, if you were to hear this sentence and to interpret it, and you want to make sure that you have a safe interpretation that is not going to be false or incorrectly true, if you always interpret the sentence as everyone loves someone, as someone being a particular person, uh, technically you would never be you would never have a false positive. You're probably not going to get the correct interpretation all the time, but mathematically speaking, you would never be um, saying something correct when you're actually incorrect. It doesn't really help in terms of processing, but if you're playing on a technicality, it's kind of an interesting language fact. So a couple new terms there, but again, this is really just review of the stuff we've already seen before. So what's really more interesting is, how are we going to do this in our syntactic trees? Well, to figure out how to do that, there's two things that we need to look at first. The first thing is ambiguity in general. So our assumption is that when we have some sentence that has multiple meanings, that means that it has multiple structures, or it at least has different versions of the tree in some circumstance. So if you have, say, John saw a man with a pair of binoculars. So this is a syntactically ambiguous sentence or semantically ambiguous sentence that is also syntactically ambiguous. So with a pair of binoculars is either going to describe the man. Oh, you're seeing a man with binoculars. So uh, the man is holding binoculars, or uh, John is the one seeing the one with binoculars. So two meanings and two structures. Where is that prepositional phrase attaching? The second sentence, competent women and men hold all the good jobs in the firm. Well, competent is an adjective, and the question is it describing just women, or is competent women and men describing the conjunction of the two? Is it saying competent women and men? So is it a case where you're doing an adj and a noun, or is it uh, and an n first, and then an adj attaching after? So two different meanings, and then there's two different syntactic structures associated with it. Now, with scope ambiguous sentences, we have two different interpretations as well. So we should have two different tree structures. But how do we do two different tree structures with a sentence like everyone loves someone? I mean, these are three individual words. We have a subject, a verb, a direct object. There's nothing we can really do in terms of attachment ambiguity. Like, it's not like we can change where these appear initially in our tree, um, or what these attach to. We can't just make someone like an adjunct, for example. That doesn't really make any sense. Um, it's not like loves is doing any changing. Uh, if we have a sentence with a lexically ambiguous word, like I went to the bank, for example, and we see that, bank has two meanings. Well, in a sentence like this, really what happens is the tree doesn't change, it's just the word that changes. So with lexically ambiguous sentences, we don't see different tree structures, we just see different words. So um, but that's not really what's happening with scope ambiguous sentences either. It's not the meaning of a word that's changing. Okay, so we need to get two different tree structures out of scope ambiguous sentences somehow. But there's not going to be a way to do this in the syntax part of our grammar system, the thing that's spoken out loud. We have to do things behind the scenes. So what do I mean by that? Well, this might not be a picture that you've seen or heard discussed, unless you've taken upper division linguistics courses. I'm not entirely sure. But this is a general assumption of how our grammar system works. So in generative grammar, this is what we assume. So we start at the top. So this is like what's in your head. Okay, so we'll start at the top. You have lexical resources. So you have a bunch of stuff in your head. This is where the words come into play. This is where you have your rules for how things work. So you want to construct a sentence. You have to pick things out of your head. Now, at this point, you might also call this deep structure. So you lay the foundation for your sentence, for your expression in deep structure from your lexical resources. Now, what happens once you've set that up is you do syntactic derivation, or this is called movement. Another way of thinking about this. Movement, doing any agreement, everything to make your sentence grammatical in the proper word order. So this is where you do things like word order. Yeah, let's just say word order, just to keep this simple. So you do word order, and now your sentence is in surface structure. So surface structure, surface structure is the natural order of the sentence that is spoken. So when you have a question, this is the normal question that you would hear spoken out loud. So what happens is that when a sentence is in surface structure, it goes into two different routes. It goes into what's called phonological form. So this is what's spoken out loud. So in a conversation, here's my person. I know what it looks like. It's a person's head. So this is what's spoken out loud. If you have a sentence that goes, someone says it. That's one path. So that's the speaking part. But on the other side, it goes down another path as well for interpretation. So once a sentence is formed, there is a pronunciation and there is an interpretation. Now, for the interpretation path, there's some more movement that can be done. But the special part about this movement is that it is covert movement. So what covert movement means is that it's unpronounced. So when a sentence is at surface structure, that's the thing that's pronounced. But the sentence has already been pronounced at this point. So anything extra for interpretation, you don't have to say out loud. So all of the movement at this point for interpretive purposes, you can mess up the word order as much as you like. I shouldn't say as much as you like. It still has to be motivated for, actual reasons. But we can mess with the word order for interpretation purposes. Covert, so it's unpronounced, it's hidden. And then we get to something called logical form, which we call LF. This is where interpretation is done. This is where we get the meanings of our sentences, and then we perform semantics on that. So you have your pronunciation branch, and then you have your interpretation branch. So usually in a course, like in 220 or in 322 or in any of your syntax courses, what you're really focusing on is this top branch, the lexical resources to surface structure. And what we've been doing in this course, it seems like we've been in the same place. But really, we haven't been doing any movement. We've actually been spending quite a bit of time in this area right here in logical form. But as of this point now, because we're starting to do movement for scope ambiguity, we're actually going to be spending a little bit more time between surface structure and logical form. So that's why we're not going to be concerned with a lot of the crazy movement that happens in the other syntactic courses. We're just going to assume a simple structure and do some extra movement for a logical form. So sorry, this part is a little bit abstract, especially when we haven't seen movement yet. And of course, talking about the model of the grammar is always going to be abstract too if you haven't heard anything about the model of the grammar. But we'll see some examples of this. So yeah, so we're going to take sentences that are in natural word order. We're going to do some movement to interpret sentences, and then we're going to conduct our semantic composition on them. So are there any questions so far before I show you how scope ambiguity works? Okay. So let me get my face out of here. Okay, so when we have a sentence, everyone loves someone, I'm going to draw the regular tree in the middle. So we're using NPs now. We'll talk about the actual system of grammar that we're using at the beginning of the set of next lecture slides, which we'll jump into very soon. So don't worry too much about the specifics of this one because we'll get into the actual grammar soon. TJ, sorry, I shouldn't be using T's at this point. So this is everyone loves someone. So here's the original sentence. A subject, a verb, and an object. Everyone loves someone. Now we need to get two different interpretations out of this. Now, if you remember what we did in logic and why we showed the case where we took our subjects and objects and took them and extracted them to the front of the sentence, that wasn't really just a translation tip. That was also incredible foreshadowing for what we do in our syntactic trees. We really do the same thing. So we can take a look at our subject and object noun phrases here. And our scope ambiguity, our new syntactic trees, what's going to happen is we're going to move these things to the front of a sentence. And depending on the order that we move them up, we're going to get different interpretations. But how do we move them up? That's the question, because we don't have any extra nodes to move them up into. So we're going to go through this process called quantifier raising, or QR. And what quantifier raising lets us do is it lets us create a new sentence node. So what's going to happen is, I'll move this over just a little bit. So let's say we're going to do the for all x version first. All x exists to y. So what we would do first is we would move the existential someone up first. Okay, so what we can do is we create a new S node above our S node. This is what quantifier raising lets us do. And it lets us create a new noun phrase to host our quantified phrase. So in this case, someone. We just call these NPs. Okay, so what we can do for movement is we simply take our word, someone, and we move it up into that new position. And we leave a trace behind. So we need to know where that word came from, and we need to know where it's gone. So in this case, I can use a number, I can use a letter. So we use a T for a trace. And in this case, I've used the letter J. So this just means this is trace J. So I could use trace 2 or trace J or trace K or whatever. And I also index this NP above with J. This way, I just know that these two positions are linked. It's sort of like using a Y in predicate logic. So exists a Y, person Y, and then X loves Y. It's the same idea. So now we know that this object has moved up. And now to finish off scope ambiguity, we want to get the full interpretation. We just have to perform quantifier raising on our subject. So we still have this subject here. So what we can do is we can create a new S node. We create a new noun phrase. So let me not overlap with this tree here. Let's create a new noun phrase, hosting site for everyone. So, okay, so we take everyone here in the subject position, we move it up. Okay, and then we leave a little trace in its place. I'll use I to be consistent with the other trees. We give this new hosting noun phrase an I, so that way we know they're indexed. And just to illustrate this, I'll just put the two little lines under, so that way we know they're connected. And we could draw a little arrow there, just to symbolize that that is moved. So now, this looks a lot like our predicate logic translation. And actually, this is the same as the tree on the left. So if we take a look at our left tree here, this is now the same one. So for the sake of space, I will now just make that really small. So it's still on this page, but the tree on the left is exactly the same. Okay. So let me just draw these arrows in, just so if you want to actually see the movement, we can have that in. So now if we take a look at the actual translation of these sentences, uh, we could say like for all x, it's difficult with the words like everyone and someone to translate this. So I'm just going to use the word person. So for all x, person x, then uh, there exists a y, person y, and loves x is a person and y is a person. So if we take a look at our syntactic tree and we take a look at the translation of our scope ambiguous sentence, we see like a very clear parallel between the two. The tree matches the translation almost exactly. So we see the connection between everyone being up front. We see the connection with someone being next in line. And then we see the original predicate, X loves Y, being that original sentence at the bottom. So if we want to do the scope ambiguous sentence for the other tree, or the other tree for the scope ambiguous interpretation, it's going to be the same process. So let me just get rid of those 3 arrows there, or 3 circles. So we won't go through the entire process again, but I will draw the arrows. So if we want to do exists a y for all x, instead of moving someone up first and then everyone after, instead what we do is we move everyone up first. So everyone is in the lower position. And then we move someone up after. So someone is in the higher position. And if we just take a look at the 2 arrows that we have between the 2 trees, I mean, we can see the difference between the movement there. And if we did the translations into predicate logic, we would also see the difference between where exists a y person y and for all x person x was. So this is how we can do scope ambiguous trees. So what I want to say again, just to emphasize, is that this is done after we say the sentence out loud. So we say everyone loves someone, that's pronounced, and then movement is done after to get the 2 different interpretations. So this is theoretical. This is not what is done in your head. I just want to emphasize that. There's quite a few people in cognitive science here who want to know how things work in the brain. This is not how it works in the brain. It's just a theoretical implementation, a computational implementation of how semantics and meaning is computed. So no, this is not how it works in the brain. This is just how we compute meaning computationally. We'll take a look at how we can do rules with determiners. So like all, some, every, and not just have single words like someone and everyone. And we'll do that in the next set of lecture slides, which we'll be doing today because this was a very short set of lecture slides. But are there any questions with how to do these ones? Okay, so I just want to show one difference I have on Canvas. So here I'm just using like S's, different S's. On Canvas, if you look, I use like S prime and S double prime, and sometimes you'll see me use like S1 and S2 for different sentence levels. Um, if at this point, because the ones and the twos are going to relate to traces with movements on trees, uh, the node labels that we give don't always look as nice as they would with the previous trees that we did. Um, so sometimes we will be using primes or double primes to signal that they are different nodes rather than ones or twos. Um, so sometimes I use NPI or NPJ or NP1 or NP2. It's just because of the fact that we have traces now. So don't worry too much about like the numbers or letters that come after nodes and on like S's and VPs and VTs, but the letters or numbers that come after NPs now are very important because those little numbers that come after NPs tell you, uh, like what was linked. So like NP with T1 and NP1, like this is important information because if you see NP1, this means that whatever T1 was is now in this position. So this one now has meaning that is beyond just like a node label. Uh, but if we see like a one under an S node, it doesn't quite have meaning like the NPs do. So uh, not all the trees I can give you on Canvas can have arrow nodes, especially if they're in questions. So we just have to rely on the traces for that kind of thing. It's just a bit of a warning for some of the notation that you'll see in some of the Canvas questions. Yeah, and on the Canvas page too, if you want to see both translations and the trees with every student and some pi, these are here as well. And these illustrated perfectly, just like the slides. Okay, back to lecture slides. So that's it for scope ambiguity. Of course, we'll see it again when we do the actual truth conditional meanings. But for now, let's take a look at some more interesting compositional trees. So today we're not going to get too in-depth into these. We're just going to cover the syntactic rules and the semantic rules, which again is no easy feat, just because we have some assignment function replacements in our rules now, which make them a little bit more complicated. But um, if you understand the predicate logic translations, this part of truth conditional meaning is a lot easier. There is an incredibly tight relationship between predicate logic and how we do our truth conditional meanings. So um, if you're having some difficulties with this stuff, it actually benefits you to spend some more time with predicate logic as well. So when I go back and work on finding some more practice questions for predicate logic, uh, it will pay to practice those and work on those uh, to help you with this material as well, and vice versa. Okay, so with our original trees, we worked with a fragment called F1. And F1 was very boring because we can only do sentences like, it is not the case that Sophie liked James, or it is not the case that it is not the case that Solomon likes David. And, those sentences were not very interesting. We didn't have determiners. We just had like three different conjunctions. Uh, well, two different conjunctions, and or, and then we had a negation. We had some transitive verbs, ditransitive verbs, intransitive verbs, and some proper names. Well, with F2, we're adding some new things. We're adding determiners. That's pretty amazing. We're adding common nouns. So words like dog, cat. That's also very exciting. We're adding pronouns. So we won't add these right away, but we'll add these a little bit later. We're going to figure out how to add things like adjectives. So that's not something I give you in lecture. Um, Possibly things like CPs and PPs too. So one of these things at least. Um, and of course, well, yeah, determiners really is the big thing. Determiners open up a huge passage into a wide variety of sentences, which also lets us deal with uh, scope ambiguity. And dealing with a type of ambiguity is really like a monumental task. I mean, once you can deal with scope ambiguity, we can now deal with every type of ambiguity that we would need to. Uh, which really, when you have a system of semantics and meaning, that's really a goal. I mean, that's huge. Imagine a system that can't deal with every type of ambiguity. You can't call it a semantic system, but at this point, now we can do it. Okay, so here are the rules that we have now. And again, we don't have that many rules. That's fine. We can still do quite a lot with them. So you'll see the introduction of the noun phrase. So I'm not going to draw all the rules. I'll just draw the new ones. So we now have S going to NP and VP. So we have NPs because we're going to have different types of noun phrases. We don't just have proper nouns. Okay. We're still going to have S conjunction S, and we're still going to have negation S. That's normal. We're going to have a VP that goes to a transitive verb and a noun phrase. So again, we'll have NP objects as well. We're not going to do ditransitive verbs. We could do ditransitive verbs at this point, but we already looked at those in F1. They would work the same way as they would in F2, but at this point, it just takes a little bit more time. So we're not going to include them, but we know how to do them if we needed to. Now, as far as the different noun phrase types, we have NPs. So these are proper names, and we know how to deal with these. They're the same things that we've done before. So now we just have this extra layer called an NP, N lowercase p to stand for proper names. If you want to call this something else, like if you want to call this an NPN or something, that is fine. You can use whatever label you want. Just make sure that it is distinguished from an NC and an NPro. We have an NP going to an NPro. This is for pronouns. We won't be using this right away, but we will be using this a little bit later, so sometime next week. And then we also have an NP that consists of a determiner and a NC. So NC stands for common noun. And common nouns, so I have different examples of all of these different types of nouns up here. So common nouns are things like book, fish, man, woman, student, and so on. Things that are nouns, concrete or abstract in the real world. Sorry, not abstract. Common nouns are not abstract. They're physical things in the real world. So these are the new syntactic rules. And we also have a rule for quantifier raising. So this rule looks a little complicated in terms of notation, but it's really just the same thing that we did in the previous slide. So this says that if we have a sentence with some noun phrase in it. Okay, so let me take a look at the actual notation first. So this is kind of like a phonological rule, whereas in X and Y, this is just context. So this can be stuff or it can be not stuff. This just says if you have an NP in a sentence, and this is actually kind of important. NP with a determiner in it. If you have an NP with a determiner in it, and there's some context around it, what you can do is you can create a new sentence node with an NP that's indexed. You can pull that noun phrase out into the new sentence node, and you can leave a trace in its place. So what this looks like is, let's say you have an NP here, and there's just whatever at this point. You can create a new sentence node. Let me take the same color. You can take this NP, you can move it up into the new position, you can give it an index I, you can leave a trace in its place. So this is what that rule is saying. And behind my face is just a little squiggle there with nothing there, saying there's context. So this is what the quantifier rule lets us do. And specifically, what the quantifier rule tells us is that if we have a noun phrase with a determiner, we have to do it. So even if the sentence ends up in the proper word order or that we need for interpretation, if we have a sentence like S, like in our original sentence, we still have to do quantifier raising. But this part is very important. If you have, say, just a proper name, the proper name does not undergo quantifier raising. If you have a pronoun, the pronoun does not undergo quantifier raising. The key word is quantifier. So that determiner will be a quantifier in this course. So some, many, all, every, even the word the is a quantifier. In the way that it works, we may encounter it, we may not. Depends on which questions are in assignment 6 and how much time we have for that. Okay, so these are the new rules that we have. So let's see these rules in action. So here's the sentence, Sam saw a movie. And what I've done is I've translated the sentence into predicate logic because I want to show the parallels between the translated sentence and the logical translation. So sorry, the translated sentence in logic and the tree structure. So Sam saw a movie. So I'm going to draw the original sentence because this is the sentence after everything has moved. So we start with an S, and we have a noun phrase that consists of a noun with a proper name, and this is Sam. We have a verb phrase that consists of a transitive verb with saw, and then we have a movie. So this is another noun phrase. We have a little bit more elaboration on our categories. So is a determiner and movie is a common noun. So this is our original sentence. Sam saw a movie. Okay, but this isn't what the final tree looks like in terms of F2. So this is, and if I relate it back to what we talked about in scope ambiguity, this is surface structure. So this is the sentence that we say out loud, essentially. We take this structure, this string of words, and we pronounce this word or this sentence, and this is what people hear. It's this proper order. But now we need to take this to logical form. to semantics for interpretation, so we can figure out what the meaning is, theoretically. Okay, so to do this, we need to look at the tree and we need to ask ourselves, do we have any quantified noun phrases? So any noun phrases with determiners in them that have quantifiers like some or all. And we see one, we see a movie. So we need to do quantifier raising on this noun phrase. So what this means is we need to make a new S node. So that's something that has to be done. And we need to create a new noun phrase node and give it an index. So let's call this one NP1. Okay, so what we'll do is we'll take everything under the NP here that we're moving, and we'll just drag it up to the new position. So we're taking a movie from down here, and we're just going to raise it up into this new position, NP1. We drop it off, and in its place, we're going to leave a trace with the same index. So NP1 there with trace 1. So we know where it came from and where it went, and this is our final tree structure. So this is how we can interpret it. So a movie, Sam saw T1, and T1 is a movie. So now we see that these two trees are the same. So this is the same tree that I drew on the left, but on the left I went through the process. So if we look at the predicate logic translation for the sentence, this now matches our tree. So Sam saw a movie, we would say, yeah, exists in X, movie X, and saw. Sam is a proper name, it stays in place, but X is a movie, so X moved up. So exists in X, movie X, and Sam saw X. And that's exactly what we have in our syntactic tree. And that's because the predicate logic interpretation and our logical interpretation to the tree are going to be very similar. So our syntactic tree is going to match our predicate logic interpretation. So once again, if we just take a look at the parallels here, the only thing that you don't see in these trees is, where that connective comes in, whether it's an and or whether it's a conditional. That part is not going to be part of the tree. That's something you have to understand from predicate logic, but the words themselves and the predicates are going to come directly from the tree. So you'll have some time to do the practice problems after the break. I want to give you the break first, but are there any questions about this tree before we take that break? Okay, it seems like the syntax trees are really good then. Let's take a 10-minute break then, and I'll see you again at 11:30-ish. And we'll do the 2 practice questions and then introduce the rules. So I will see you then.
Over here to this blue zone, a less pleasant place.
A TED Talk with Venn diagrams. That's beautiful. Anyway, let's try some practice with these tree structures. So we have Kate read every novel, and we have some person saw every performance. So Kate read every novel is going to be quite similar to the tree that we see here. And some person saw every performance is going to have two trees. It's going to be scope ambiguous. So there's two ways you can do the tree. You can always draw the surface form first and then draw a second version with movement, or you can just draw the first tree with movement already in. It's up to you. I don't need to see the surface form and the moved form. I just need to see the moved form. That's just a heads up. But however you want to do it, it's up to you. So if you want to try this, go right ahead. I'm going to pretty much do it at the same time, but I'll give you a 3 minute, or I guess a 2 minute head start on me. So here's a 2 minute head start, and then I'll start working on the trees as well. If you have any questions, again, interrupt me at any time, or just ask over voice or chat, and I'm happy to answer. Okay, so Kate read every novel is going to be very similar to Sam saw a movie. So I'm just gonna build the movement straight into it. So we're gonna have an index here. Okay, so specifically every novel is going to move up. So we're going to get every novel at the top of our tree, every novel, and then we're going to get into our original sentence. So Kate is going to be our subject. Read is going to be a transitive verb, but then every novel is our original object, and that will have moved from its position. So uh, we have T1 as a trace, NP1, and essentially we're getting movement from the object position to the very front of the sentence. And if we were to translate Kate read every novel into predicate logic, we would get for all X, if X is a novel, then read Kate X. And if we take a look at our tree structure, this is really what we get. For all X, or for every novel, Kate read X. So we can always check the predicate translation to see if our tree structure matches it, or vice versa. So you can use the syntactic tree as support for the predicate logic translation, or vice versa. So I'm going to get rid of the arrow here, but I'm going to move the translation down here just to keep that on screen. Okay, for the second sentence, some person saw every performance. Uh, again, we have a scope ambiguous sentence. So let's start with the base tree. We'll do one set of movements, and then we'll do the second set of movements. So some person, this is a determiner. I'll write this out neatly. Some NC is a person. We have a verb phrase with the transitive verb saw. And then we have another noun phrase, every performance. So there's a determiner, every. Let me get rid of my cam for this because I'm just going to be taking up real estate. NC, this is the word performance. Okay, some person saw every performance. Now, which translation do we do first? It doesn't really matter to me. Let's just pick one to move up to the top first. So I'm also going to need to make this whole, have to make this whole tree a little bit smaller just for the sake of space. Okay, so the first thing I'll do is I'll make a new S node. I'll make a new NP node. I'll give this a 1 label. And let's just move every performance up first. So I'm going to take every performance. I'm going to move it into the new position here. It's moved up into NP1. So I'm going to leave a trace T1. Okay. Make a little bit more space. So there's one movement. Now we have to do another movement. So in this case, let's make a new S node. Let's make a new hosting site NP2. We have one more quantified noun phrase, some person. So let's take everything under some person. Let's move it up into this new site. It's gonna move things around a little bit. And then we'll leave a trace in its place. So now we have some person, every performance, T2 saw T1. So yeah, I gave T2 to some person and I gave T1 to every performance. Again, it doesn't really matter what subscript I give these. I could have given T1 to some person and T2 to every performance. What matters more is that I know which one moved from which position. So this is the interpretation where some scopes over every. That's what interpretation this is. So if we were to translate this, and at this point I'm going to get rid of this tree for space. If we were to translate this into logic, it's gonna make that a little bit smaller. We would get something like, there exists an X, person X, and for all Y, performance Y, then saw, and which one saw which? Well, the person X saw the performance Y. So this translation matches our tree structure. And if we wanted to do the other one, the other tree structure, I'm going to take the liberty of copy and paste, and then I'll give you a little bit of time to make the adjustments yourself. Instead, what would happen, the traces would be in the same place, but the some person and every performance would be in different positions. So really the colors here should be different too. So this is actually a little bit problematic. NP1, NP2. So let me just make some quick changes here. So this should be blue. And that should also be blue here. Okay, so if we take a look at the two different trees, and we'll draw our arrows in now, we can see the difference with the arrows. So in the left tree, instead of having some scoping over every, we now have every scoping over some. So every has moved to the top, and some is now narrow scope, moving into that second position rather than the first.
I don't quite get the difference in the meaning for the two trees.
The meaning of the two trees.
Yeah, the difference in meaning.
So in, okay, let me get rid of this translation on the bottom. Okay, in this first tree, okay, let's do the tree on the right first. The tree on the right says there is a particular person. So here's the person, and here's a bunch of different performances. This person saw all of those performances. This person has seen every single performance. In the tree on the right, this one says that for every performance out there, some person or other has seen it. So there could be multiple people out there. This person has seen this performance and this performance. This person has seen these two performances. This person has seen these two performances, and so on. So it's the same interpretation that we've seen before. The right one focuses on a particular person first, and then all the performances after, while the left interpretation focuses on each performance. Then one person sees it or another. And the some person can be a different person. But where the confusion might be coming is that these are theoretical interpretations. So scope ambiguity says both are available. However, in English, when we see a sentence that starts with the subject, some person saw every performance, our brains, we really, really, really want this interpretation in English. When we have a subject, some person, this is what we want. Compared to if we had like every person saw some performance. So we have an incredible bias towards this interpretation, and this one is very, very hard with this sentence configuration. But the semantics say that both are possible. So that's why the meaning on the left is maybe a little bit difficult to interpret or hard to get. It's because your brain doesn't really want you to get it in English, but it is available. In some languages, there is scope ambiguity, but one interpretation just literally never happens. So languages can be categorized in that way too, cross-linguistically. Like when you have two different scope ambiguous interpretations, which ones can speakers get? And you can classify languages in that way. So that's more of a cross-linguistic thing and not really the focus of this course, but that's just another little fact about languages. Okay. So I'm guessing because everyone seems so good with things that there weren't too many difficulties with these, but are there any comments or questions about these structures or anything that might come up in the future?
Could you also write the translations for the second tree as well?
The second, so the logic one, yeah. Let me get rid of the little people on the bottom. So the second one would start with performance. So I'll try to use the same variables for all y. If y is a performance, I'm just going to shorthand this. Then, where's blue? Then there exists an x such that x is a person and saw, well, who saw what? X saw the performance. So same thing as the last one, except for all y and exists in x have swapped positions. So that matches the tree as well. So close, very close, Bradley. You just have to make sure that the arguments in saw are in the correct order. So in that translation, you have the performances seeing the people, but the people are seeing the performances. So the subject has to be first in saw. So that's why, like in this case, I have two being the subject here, which I said it might be a little bit weird that I chose that, but again, the indexes are just arbitrary. So it just matters which matches which. So in this example, 2 is the subject. In most cases, you would pick 1 as the subject because you just use numerical order, but it doesn't really matter. I could have picked T Z if I wanted, or T 300. It wouldn't have made a difference. They just have to match. But in this case, X is the one seeing. And that matches some person as a subject. Okay. So we might not get to the one quantifier tree today, which is totally fine, because just the rules themselves are quite, I don't want to say they're difficult rules, but they are, they're just as notation dense as the rules of F1. In fact, they're a little bit more notation dense than the rules of F1. So let's talk about some of the rules that we have. And the nice thing about the rules of F2 is that we're still keeping the rules from F1. So everything that you've seen before, it's still going to be the same. So when you have like a pass up rule, like if you have like an NP to an NP, when you take a look at the meaning of this, let's say this is J prime, and you're asking yourself, well, what's the meaning of the big noun phrase? Well, it's just going to be the meaning of its child here. So that's the rule, and then that's the value. So the pass up rule is still going to be the same. If you have a negation with a sentence, we're still just negating the sentence. If you have a conjunction of two sentences, we're still just applying the conjunction in two sentences. If you have a sentence with an NP and a VP, it's still the same thing. It's true if the noun phrase is an element of the verb phrase. If the semantic value of the noun phrase is an element of the semantic value of the verb phrase. Let me get my camera on so you can see my hand movements that don't actually help with learning at all, but they're there to make it feel like I'm doing more than I am with my voice. And then with the transitive verb, same thing as well. you have a transitive verb and you have an object, again, at this point, you're looking for pairs x, y. You get your y, you plug it into the y value, and now you're just looking for x's. It's the same concept as before. The only difference in the notation is that before we were just looking at a situation, but now we have assignment functions. So we replaced v with m and g. So m is the model. It's like our universe that we're looking at. It's our situation. And g is our assignment function. So G is going to be for our quantifiers and binding. Okay, so everything you've seen before, it's still going to be the same. So all that stuff we did with F1, we're not throwing it away. We're not starting from scratch. We're still continuing with it. So when you get your test back and you get comments, by the time you actually work with real examples, you'll be able to look at that and review that and see where you went wrong. And you'll get to recover from it essentially and get feedback and actually incorporate it in with this lecture. Okay, so what about new stuff? That's the important stuff, new stuff. Okay, so the new things we have first are traces and pronouns. So we're not going to deal with pronouns yet, but I'm going to show you how they work because traces and pronouns are going to work identically in our trees. So traces and pronouns are actually quite easy for us. So imagine you encounter anything that's like a T1 or say he one, and what you'll notice with pronouns is that they all have little indices with them. So they'll have little numbers, just like on our assignment function. So that way at the end, we know like who he or she or it or they is. Now, we don't actually know who this is. The assignment function, remember, it's G. G tells us who these people or traces are. That's the function of G. And G is the function. It's the function of the function G. So in our tree, when we talk about the meaning of these, let's just zoom in. The value that we give to it, we just apply the function to it. That's the value. The meaning of the trace is just the function applied to trace. We do not evaluate until the very end. So that means the very, very end of the tree. So whenever we see T1, we leave it as GT1 until the very, very, very top of the tree. So T2, same thing, G of T2, very, very top of the tree, then we can change it. So whether it's a trace or a pronoun, it's going to work the exact same way. And here's just the pass up rule shown. So imagine we have an NP with the trace one. We'll always see this usually. So if we have a trace, we have a noun phrase directly above it. The noun phrase just gets the same meaning. It's a trace. The noun phrase gets the same meaning of the trace, G of T1. It'll be, so the same thing with a pronoun. No, with a pronoun, we don't know who G of she is. The assignment function tells us. But we don't evaluate it till the very end either, because pronouns might be bound. They might be free. We don't know. The tree might bind a pronoun at some point. So we don't want to evaluate the pronoun until the very end of our derivation. So evaluate at very end may be bound. So if we see something like she won or they won or he won, we just leave it in the assignment function form. So this is G of she won. And again, this just passes up. So at the very end of the tree, we might eventually say, okay, like this is Kayla prime or something. If she is Kayla, then it's Kayla prime. If she is Teresa, it might be Teresa prime. But as we work throughout the tree, we just leave it as G of she1. So, I mean, this advice may be bound, really works for both of these. Both of these traces may be bound. In fact, the traces will like always be bound because there has been movement with a quantifier, so the traces will be bound by the end of it. But pronouns can be free.
What does the otherwise A, B, MG equals VB mean?
This is just sorry, this otherwise A, B, V, B. This just means that otherwise you have regular predicates that would be evaluated as usual. Evaluated as normal. So this just means that if you have something like a VT with love, you would just evaluate love as if it were the lexical item love. So it would be the set of XY such that X loves Y in M. So if that last category is a pronoun or trace, it gets the assignment function. If it's not a trace or a pronoun, it's treated as like as a lexical item. And gets like a set notation or gets an element notation as like an object like Steve or Carol, or it's just passed up. So maybe not just predicates, but predicates, nouns, proper nouns, anything that's not a trace or a pronoun. Oh, I guess since we're here, just because I'm not 100% sure if it's in this, I don't think it is. I don't think I added it. But if we see a common noun, for instance, like dog, if we think about predicate logic, we would translate dog as something like dog X, right? So dog X is like the set of X such that X is a dog. We're going to do the same in our trees for common nouns. So for instance, when we think about the meaning of dog now, this is going to be a set. This is going to be the set of X such that X is a dog in M. So this is how we treat common nouns. We treat them as predicates, as intransitive predicates. So this is just a heads up. So when we think about concrete nouns, we think about things having the property of being a concrete noun. So like in the sentence, Fido is a dog. If Fido is a dog is true, then Fido has to be a member of a set of things that are dogs. So again, we get a lot of inspiration from predicate logic. So if we try to think like, how do we represent this word in terms of our lexical in terms of our truth conditional semantics, we can think to predicate logic to get a rough idea of, no pun intended, a rough idea of how to translate it into a set theoretic notation or into into an actual element or not.
So if we have common noun and then we have dog and then square brackets, at the right top we also write MG, right?
Yeah. So I really should include that. So MG or doc. Same with love. Okay. Now, the next two rules are for our quantifiers. And once we get those two rules down, really, we've covered all of the new stuff. And yeah, 3 new rules to cover everything. It might not seem like a lot, but it does make a huge difference in our trees. And again, at this point of the course, like a lot of it's now about self-discovering new rules using predicate logic. So there's still more to discover. Okay. So now, this is where rules change a little bit. So before, especially when we did the ditransitive tree, there was this rule that we had where we said that everything has to be based directly off of the children. So VP had to look exactly at the V bar and N. With quantifiers, we go a little bit further in. And this is only for quantifiers. So if we have a quantified phrase, the rule is actually based on what we see here. So it's based on like a mini structure. So it takes a look at what the determiner word is and what the structure is to determine what the rule should be. So it does take a look inside of the S node, which is something that other rules cannot do, but this is a special case to make quantifiers work. It's something that the system needs, which is why not everybody, in fact, most people nowadays don't necessarily use this system for semantics. There's an alternative system which is much, much more abstract that is just not beginner friendly. So this system is taught first as a way to get us to understand the mathematics and the intuition and everything. And then the other system is brought on top, because once you understand all the fundamental in mathematics, then you can go into the more abstract stuff, which treats this in a much nicer way and much more consistent way. But this digs into the structure a little bit to get a rule. So let's talk about how this works. And this is why I say that understanding the logic is very important. So I'm going to look at the implementation first and then go to the rule. Okay, so we're going to look at the sentence, every student likes here. So we want to know when this is true. So this is a true or false sentence. Now, what's happened at this point is we've already done quantifier raising. So it was every student likes Kier, but we moved this up into a higher position. So this is now like a new S node above the original S node. So for all X, if X is a student, then likes X Kier. Okay. So basically S NP1, S, we have a determiner and an NC here. We have a noun phrase with our original trace, verb, and so on. So we had our movement up to this point. Okay. So I'm going to make this smaller if I can. My writing utensil. Okay, so let's take a look at how this is implemented. So I'm going to rewrite this. This is every student, and this is T1 likes Kier. Okay, so first of all, let's take a look at S1. So this is sort of a refresher, and this should look like what we're familiar with. T1 likes Kier. So this looks like what we had before, except instead of a name here, this is our trace. Like T1 is a trace. T1 likes Kier. G of T1 is in the set of X such that X likes Kier and M. If we said Kayla likes Kier, we would know if that's true because we'd say Kayla's in the set of X such that X likes Kier. The only difference between now and then is that we have a trace instead of a proper name. But we've seen this before. It's just G of T1 instead of a proper name. Okay, and now we want to put every student in there as well. So first of all, I want to write the predicate logic translation above. So every student likes Kier. Let's do this in Greek. For all X, if X is a student, then likes X Kier. Okay, this is the translation of that sentence. Now, I'm just going to read for you what this says. This says, it's true if for all D in our universe, so for all variable D in our universe, if D is a student, so if D is in our student set, then our original sentence where D replaces our trace is true. So in other words, the trace is being bound here. Okay, so let's spell this out. So it's true if for all D in our universe, if D is in the set of X such that X is a student, then D is in the set of X such that X likes Kier. So if we think about the predicate logic translation, this rule matches quite nicely. For all D in our universe is like saying for all X, if D is in the set of X such that X is a student, okay, student X, then that's our arrow. D is in the set of X such that X likes Kier, which is like saying X likes Kier. Okay. So I just want to talk again about that second line, and then we'll go to the rule. Just having that concrete application of it first. So if for all D in our universe, if D is in the set of X such that X is a student, then D is in the set of X such that X likes Kier. So if we take a look at this first line in more detail, we say S1, M, G, and D replaces T1, and this is true. So this is what this top line says. And I want to focus in on the fact that D is replacing T1. Okay. So if we compare this part here with this part here, remember, this is S1. And what we're saying in our first line is that S1 up here, S1 is true where D replaces T1. The substitution that's being made is that G of T1 is now bound, so D is replacing G of T1. This is what's happening here. This is the substitution that's being made. This is where the binding is occurring. So instead of G of T1 being in the set of X such that X likes Kier, now we're saying that D is in the set of X such that X likes Kier. But it's not, sorry, I want to make sure this part is still here. But it's not just the fact that we're replacing G of T1 with D, because it's more than that. It's being bound. We're also adding the fact that D is a student. So this is where the binding is coming in. We're connecting the fact that D is a student and D is the one who likes Kier. So we're connecting the fact that it's a student who likes Kier and not just some random individual or just some random noun. It's specifically everything that is a student is the thing that likes Kier. So it's also what's happening here when we do this for all X and we link student X and Kier X. So this binding relationship in our assignment function in our rule is the same thing that's happening with the predicate logic translation when we do the for all X. So like this is not, I don't think myself that this is beautiful notation. I think this is a little bit of a messy notation, and I don't think the parallels are very clear at first. But again, the more you do it, and when you take some time, and I really do mean like, I this isn't the fastest thing to grasp. If you did grasp it fast, congratulations. That's great. If you haven't, sometimes it takes 5, 10, 20 minutes to go over it yourself slowly and just go through the notation bit by bit to get it. And I recommend it. So what I want to do now is actually just take a look at the rule. So for the universal, in fact, let me just take this here, copy, and put it down here in a place that's a little bit less busy. Okay. So every B or S, so this B here is just like a common noun. So every noun in a sentence is true. So this is just a quantified sentence. If for all D in our universe, so this is like corresponds to for all X, if D is in whatever that noun is. So if you have a common noun as a predicate, then whatever the sentence is true where we do binding. So this is binding X. So that sentence would be true. So for example, this would be like, Kate saw every performance. So for all X, if you did performance X, then, sorry. Then saw Kate X. This binding part, this GTI is really the equivalent of what's happening here with the for all X with binding. So in terms of like a tree structure with this rule, what we'd have is something like, sorry, equals 1 if for all D in our universe, if D is in performance and G, then whatever S was with Kate loves every performance, with M, G, D, with whatever our thing was, would be true. Let me actually move this all up again. So I'm sort of doing this without the tree here, but just to give you an idea of how Kate loves every performance would work out. And again, I'm just going to move my webcam off here. So this is true if for all D in our universe, if D is in the set of X such that X is a performance in M, then D is in the set of X such that Kate saw X in M. So what's happening here in this case is in our truth conditions, we're saying if D is a, so first of all, for all D, so this is where the universal comes in. If D is a performance, then D is in the set of X such that Kate saw X. So again, this is the object, and we're saying that D, all of the performances, is what Kate saw. So that one is without a tree, but just to really show you the parallels between the predicate logic translation and what the final result comes out as without an actual tree structure there. So again, just to reiterate, I don't like harping on difficulties or confusions all the time, but if this is confusing at first, that is normal. It does take some time to get used to these rules. So for all of the different trees and types that we're doing, there is practice with a new tree on Canvas. So you do have extra practice questions for F2 compared to F1. Are there any questions about this rule? Okay. I mean, there's only 2 minutes left, but and we can talk about this again next time when there's a little bit more time to digest. But if we take a look, and I'm just gonna sort of go back between these two slides back and forth for some versus every. If you just take a look at the top, for some D in the universe, D is in the noun and S, compared to for all D in U, if D is in the noun, then S. There's really not much of a difference between these two types of rules. And if you understand the logic, you'll understand why the two rules differ very subtly. It's because for the sum translation, we know that with the sum translation, there's a noun and there's whatever is left. So we use the and. So that's why we say for some D in our universe, again, B is just a common noun, we use and then we do our binding. So again, the rules match the predicate logic extremely closely. So if we have the sentence, some student likes Kier, well, if we take a look at our rule here, we're saying for some D in our universe, D is a student and the sentence with binding is true. So for some D in our universe, D is a student and D is in the set of X such that X likes Kier. So the only thing that's really changed between every and some is the fact that we have some D and we use the and instead of then or if then, because we're looking at the existential instead of the universal. So we can take a look at this again on Friday if you'd like. But again, these two rules just follow the predicate logic exactly. So if we spend a lot of time on the every, we don't need to spend that much time on some because the logic is very similar. But that is it for today. If you have any questions, you're free to stick around and ask them. But other than that, that's all there is today. On Friday, we'll take a look at a full tree. We'll take a look at a couple full trees for examples to see how these work. And then we'll continue from there and we'll be done with this lecture hopefully on Tuesday. But yeah, I'll see you Friday. Can you go back to the slide with semantics of F2 rules from F1? Yes. Enjoy the rest of your day.
Thank you.